Hello everyone, good morning. Thanks for coming to another FLAN talk. Today we have Ruizhong, who's a graduate student at UIUC. He's interested in ML for graphs and time series, and now he's turned his attention towards theoretical foundations of language models, and we're very excited to hear about his talk. So Ruizhong, take it off.
Okay, thank you for the nice introduction, and let's get started. Uh, Today I'm gonna present our recent work, Turing completeness of prompting. So here's the outline of today's talk. So nowadays the mainstream architecture of large language models or LLMs is transformers, and there has been a series of theoretical studies on transformers under realistic abstractions. Um, So for example, previous work have shown that the class of all transformers with hard max attention is Turing complete. And for example, for any computable function, for any function that can be computed in Tn steps with one tape Turing machines, there exists a transformer that computes the function using OTN COT steps on length n inputs. And Merrill and Soberwall have later improved the COD complexity to OTN for time Tn functions. And these work have finally characterized the capacities and limits of transformers under the class of one model, one task paradigm. And however, in practice, the existing theoretical studies does not align with the LLM prompting practice, or let's say one model, many tasks paradigm. So in the era of LLMs, people train a single general purpose LLM and provide the LLM with different prompts to perform different tasks. And since the success of GPT, the LLM prompting paradigm has revolutionized machine learning. So in such empirical success calls for a theoretical understanding of the LLM prompting paradigm. So we are interested in how powerful is the LLM prompting paradigm. And in this work, we present a theory on the LLM prompting paradigm. And in particular, we show that prompting is actually Turing complete, which in the sense that there exists a finite size transformer such that for any computable function, there exists a corresponding prompt following which transformer computes the function. And we not only show existence, but also give a simple and explicit construction. And furthermore, we show that prompting is not only universal, but also efficiently universal. So even though we use one finite size transformer, it can still achieve nearly the same complexity bounds as that of the class of all unbounded size transformers. And then we characterize the COT complexity and the precision complexity of our construction. Here's a technical overview of our work. So the main question we want to address is that how should we theoretically formulate what prompting is? So let's just say natural languages are too unstructured. And if we use Turing machines or common programming languages, they are in some sense too complex. So we are interested in a simple mode of computation that is nearly as efficient as Turing machines. So in particular, in this work, we'll construct a new model of computation called two-tape post-Turing machines, or two PTMs for short, which can be easily encoded into a prompt using a finite alphabet. And furthermore, we show that two PTMs are not only Turing complete, but also nearly as efficient as Turing machines. And finally, let's say, so given a commutable function phi, we encode its two PTM into a prompt pi phi. Then it remains to construct a transformer that can execute two PTMs. And Yes, specifically, we use COT steps to record the execution steps of the two PTMs so that the transformer can restore the state of the 2PM at any step. This which is uh, uh, inspired by Prime. And this establishes the COT complexity and precision complexity of the construction. Okay, so let's get started. First, I'll introduce a few string notations. We'll let sigma denote a finite alphabet, and each symbol in sigma is called a token, which is commonly referred to a token in the literature of large language models. And let sigma n denote the set of length n strings over sigma. Sigma star denote the set of all finite strings over sigma, and sigma plus the set of all non-empty finite strings over sigma. And sigma to the omega denote the set of all countably infinite strings over sigma, and let epsilon denote the empty string. For strings x and y, let the size of x denote the length of the string, and f to the nth power denotes repeating the string n times, and x dot y denote string concatenation. So the computability are characterized by Turing machines according to the Church-Turing thesis. An M-tape Turing machine is defined by a septuple where Q is the finite set of states, Q start is the initial state, Q halt is the halting state, sigma is the finite alphabet of the tapes, space is the blank symbol, M is the number of tapes, and delta is the transition function, where L, S, and R denote left state and right, respectively. Okay, so according to the Church-Turing thesis, a function is said to be computable if there exists a Turing machine that computes the function for all inputs over the domain of the function. And Shannon has shown that any Turing machine over any alphabet can be easily simulated by a Turing machine M prime over the binary alphabet, sigma equal to 0 and 1, where the space symbol is 0. But although M prime uses more states, so we will assume that Turing machines have binary alphabet for simplicity throughout this paper. Here are some theoretical characterizations of neural networks. So a ReLU neural network is a composition where each basic operation is either an affine map, an entry-wise ReLU activation, or a layer normalization. And a decoder-only transformer is a composition where the first layer is called the embedding layer, which maps a token to a vector. And each then there are L layers that are called transformer layers, where in decoder-only transformer, each transformer layer is a causal attention. And finally, we have the output layer that maps the last token embedding into logits. And finally, we use greedy decoding to output the token. Yes, for the embedding layer, it has two components, an embedding map and a positional encoding map. Following common practice, given the input token sequence, the embedding layer adds a positional encoding to each token embedding. And the output layer can be abstracted as a ReLU neural network. And the embedding, given the embedding of the last token, we will use argmax to compute the output token. And the autoregressive generation process is as follows. So given an input sequence, so let W denote the input sequence and Y denote the output sequence. So initially, Y is an empty string. In each generation step, we will append gamma of W concatenated with Y to Y, so the length of Y will increase by 1 in each step. The process stops the following a so-called stop token, and finally we'll denote generate. The generated output of W will be Y. In each layer, there are multiple attention heads in the ReLU neural network. So here, there's a query map, key map, value map, and the similarity map. And the similarity score between two tokens are computed as follows. So finally, we'll use multi-headed causal attention or residual connection, following common practice of decoder-only transformers. The only difference is that we use hardmax instead of softmax following prior work. So here, the definition of hardmax is this. So given an real sequence S, if the maximum value of S appears T times, then the hardmax of the sequence is 1 over T if Si is equal to the maximum value or 0 otherwise. Okay, so here's our main result. So basically, we show that there exists a finite alphabet, a finite size decoder-only transformer, and coding schemes tokenize and read out, with which prompting is Turing complete, in the sense that for every computable function phi from its domain to binary strings, so there exists a prompt pi phi, such that for every input x in the domain of phi, the transformer, after autoregressive generation, computes a finite chain of thought. And if we read out the chain of thought, then it will be the output of phi on x. So here, sigma and gamma and tokenize and readout are independent of the function phi, and the prompt pi phi is independent of the input x. Furthermore, for any input x, tokenize and readout run in O length of x and O the length of phi x time on the random access machine, respectively. Sorry. Yeah, so here we are. So now let's get into the construction. Here we will show how to construct a prompt for any given computable function. The basic idea is that we let the prompt encode a formal description of the function and later construct a transformer that can execute the description. The construction of the transformer, we won't introduce the construction of the transformer due to the time limit, but we will focus more on the prompt. So as computability means that there exists a Turing machine that computes phi. So one might seek to encode the Turing machine to the prompt. But unfortunately, a Turing machine can have an unbounded number of states and an unbounded number of tapes. But we are only allowed to construct all prompts using a single finite alphabet and to execute all prompts using a single finite state transformer. So even though one can use sophisticated schemes to encode Turing machines, it remains highly non-trivial to construct a transformer to efficiently execute such encoded Turing machines. Hence, instead of working with Turing machines directly, Here we want a model of computation that can easily encode it by a single finite alphabet and is still Turing complete. So although a possible approach is to use an imperative model of computation, such as Wang machines and Davis-Siegel-Weyuker post-Turing machines, it is still unknown how to efficiently simulate arbitrary Turing machines using these machines. So this suggests that these models of computation might not be the best candidate for constructing a prompt. To fulfill our desiderata, we propose two-tape Turing machines, two-tape post-Turing machines, or two PTMs, which is inspired by Wang machines, DSW WPTMs, and the Henning-Stearns theorem. So inspired by the Henning-Stearns theorem, we let two PTMs use two bi-infinite tapes A and B. And each tape has the binary alphabet and the head pointing to the cell. A two post-Turing machine, two PTM is defined by a finite instruction sequence, delta, where each instruction is one of the following. Where sharp denotes halt. And tau L, where tau can be either A or B, denotes move the head for tape tau, one cell left, and go to the next instruction. Tau R is move the head for tape tau, one cell right, and go to the next instruction. Tau 0 denotes writing 0 to the pointed cell of tape tau and go to the next instruction. And tau 1 is similar. And tau exaggeration mark is if the pointed cell of tape tau is 0, then go to delta k, else go to the next instruction. And tau question mark is similar. So let I denote the set of all possible instructions defined above. Yeah. So before execution, the input is written to tape A, and the head for tape A is pointing to the leftmost cell of the input, which we call cell 0. All blank tape cells are filled with 0. Then execution starts from instruction delta 0 and halts upon instruction sharp, which is halting. And the output is the content left on the tape A starting from cell 0. So we will show in section 4. We will show later that two post-Turing machines are not only Turing complete, but also nearly as efficient as Turing machines. So yeah. Next, we will describe how to construct a prompt for a given computable function. So according to Shannon's encoding, so Shannon has shown that binary alphabet has suffices. So let's focus on binary alphabet. So to recall that two PTMs use the binary alphabet with a blank symbol being 0. So to distinguish the input symbol 0 and the blank symbol 0, we employ Shannon's encoding to translate inputs and outputs of computable functions. So for the empty string, the Shannon's encoding maps the empty string to the empty string. It maps 0 to 1, 0. It maps 1 to 1, 1. And for a string, the Shannon's encoding will be the concatenation of the Shannon's encoding of each token. And thus, we will identify 0, 0 as the blank symbol here. So here, there are a few properties of Shannon's encoding. So first, S is injective, and both S and S inverse can be computed in linear time. Then how to construct a prompt pi5 for a given computable function. So since the class of two PTMs is Turing complete, as we will show later, then given any computable function, there exists a two PTM delta that computes the Shannon encoding of the output pi of phi from the Shannon encoding of x for all x in the domain of phi. So it remains to encode the prompt, the 2 PTM into a prompt. So let's define a map P to encode each instruction, delta J. So for the halting, so for sharp, tau L, tau R, tau 0, tau 1, they are simple instructions. So we can simply create a corresponding token in sigma for each of them. And for tau exaggeration mark and tau question mark, your index k can be any natural number, but we need the alphabet sigma to be finite. So as a workaround, we use unary encoding of k minus j here. So basically, if k is smaller than j, we use minus to the we repeat minus sign by j minus k times. And if k is greater than j, we repeat plus sign k minus j times. We also use additional at mark to mark the end of this encoding. Here we have created 7 auxiliary tokens to be used by the transformer. Yeah, finally, the constructed prompt is as follows. It's the concatenation. It's the concatenation of the encoding of each instruction. And also we to help the transformer execute the prompt, we will add 2 auxiliary tokens to be used by the transformer, which marks the beginning and the end of the prompt. So here's an example. A 2 PTM for deciding the Dyke language, which is the language of balanced parentheses defined by Schutzenberg-J. So here is it's 2 PTM for deciding the Dyke language, and we can translate that into the corresponding prompt. As we can see, so we first add the beginning token, and then we translate a question mark 14 to a question mark with a few plus signs and an at, and yeah, the rest of the symbols are similar. And at the end, we append a $sign to mark the end. So here you may notice that we will omit delimiters for conciseness when there's no ambiguity. So yeah, so to achieve Turing completeness, it is known that finite size transformers without COT are not universal. So to achieve Turing completeness, we need COT steps to record the execution steps of 2 PTMs, so that the transformer can restore the state of delta at any execution step, which is inspired by prior work. So in this, here we will focus on the case where input is empty. We will describe how to incorporate the input later. So here, each execution step can be summarized as a quadruple. J, delta J, CA, and CB, where delta J is the current instruction, and CA and CB is the point itself, tapes A and B, respectively. So we will define a map C that maps the quadruple to a string, which means that we map each execution step to 1 or more COT steps. So if delta J is the one of sharp, tau L, tau R, tau 0, and tau 1, we can simply use a single COT step to record them. But if delta J is a go-to condition, is the go-to instruction, we will record whether the go-to condition is satisfied or not. yeah, so if the go-to condition is not specified, we'll use slash to mark that. And if it's satisfied, we will use a equal sign to mark that. And the rest of that is will be kept on the tape. And finally, we need to append the output phi of x after the execution steps in the COT. So here we will use a semicolon to mark a new as a new auxiliary token to mark the beginning of the output. And finally, we reuse the token $sign token to mark the end of the output. And we will put the output between the $sign and the semicolon. So finally, the readout map is simply extracting the part of the COT between the $sign and the semicolon. So altogether, we have created a finite alphabet of 23 tokens as follows. Okay, so let's revisit the Dyke language example. An empty string input is in the Dyke language, and its corresponding COT steps are as follows. So we can see that the first step is the go-to condition is that the go-to condition is not satisfied. Yeah, and other steps are similar. And finally, after the semicolon, we will have an output 1 followed by the $sign. So this means that the empty string is in the Dyke language. Okay, so now let's describe the input tokenizer. And note that the input tokenizer should be independent of the function phi and can encode any input without changing the prompt phi of phi. So although it is possible to introduce additional auxiliary tokens to represent inputs, here we provide a simpler construction that makes use of only the existing tokens. The key idea is to emulate an imaginary process of writing the input to tape A. So we will define a map E that encodes an input X into COT steps. So since two PTMs assume that the head for tape A is initially pointing to the leftmost cell of the input, we write the input from right to left onto tape A. So hence for each bit xi of the input X, we write its Shannon encoding S of xi from right to left onto tape A. And for the entire input, we concatenate the COT steps of each bit from right to left. Intuitively, EX represents the execution steps of an imaginary program that writes the Shannon encoding of X onto tape A. So to ensure that the tape A head is at cell 0 after writing the input, we first move the tape A head the size of S of X steps right, which is two times the size of X. Hence, we will define the COT steps for writing the Shannon encoding as the following Z map. Yeah, which first we move the tape head two times X steps right, and then append it to E of X. However, there's a caveat. The two PTM should start from delta 0, but these extra COT steps will confuse the transform into starting from the delta sub the size of Z of X. So the solution is to add an imaginary go-to step to let the transformer go back to delta 0. So following equation 12, so following equation, let's say, following this equation, we will reuse the equal sign and to construct the imaginary go-to step. So if the input X is empty, we will tokenize it as an empty input because there's no need to write COT steps. But if x is a non-empty string, then we will use zx appended with an imaginary goodie step. This input 01 has channel encoding 1011, so it will be tokenized as follows. And then we will use append an imaginary goodie step. So now let's introduce how to construct the decoder-only transformer. So in this presentation, we will only describe 3 core operations to be used by our transformer. And we will, the detailed construction, for the detailed construction, please see our paper due to the time limit. Okay, so first operation is Boolean algebra via ReLU activation, an equality check via layer normalization, and farthest retrieval via causal attention. So the size of the constructed transformer is constant. So here, gamma does, because this transformer gamma does not depend on any specific function. So it has a constant number of operations. And furthermore, it uses only 0, 1/2, 1, 2, and 3 as its parameters. So they can be encoded into finite bits. There are no irrational numbers. Okay, so for the Boolean algebra, it's a basic building block for checking the go-to conditions. To recall that a ReLU function is the max of z and 0. So for the AND operation, we can implement the AND operation using ReLU as follows. For u and v is equal to ReLU u plus v minus 1. And other Boolean operations can be implemented using a combination of the AND operation and the negation operation, where the negation operation is the negation of v is simply 1 minus v. Yeah, and equality next is the equality check via layer normalization. So here layer normalization is so given a vector z, if z is non-zero, then the output of layer normalization will be normal z over the norm of z. And if z is 0, we will let the output be 0 to avoid division by 0. So in our construction, we will need an equality check between 2 real numbers not equal. We're not equal of u and v is defined as 1 if u is not equal to v, or 0 otherwise. And so to implement that, we can use layer normalization. So let's say if u is greater than v, then u minus v after layer normalization will be 1. And v minus u after layer normalization will be -1. So we can then use ReLU to keep them positive 1. Yeah, so a final core operation to be used by the transformer can be abstracted as follows. So given a number sequence v, where each value is in -1, 0, or positive 1, we will want to find the smallest I such that the sum of vj through 0 to 1, from 0 to through I, is equal to the sum of the entire sequence. However, since causal attention is an average rather than a sum, it cannot compute the sum for arbitrary I. It can, nevertheless, it can compute the average for every I, but equal sums does not mean equal averages. So to bypass this mismatched coefficients here, we will use layer normalization to remove the average and coefficient. First, okay, so let's be specific. So first we will use layer normalization to compute a representation of the sum. and which removes the average. So if we only because the sum is a number, so if we only apply layer normalization to a number, it will be either 1 or -1, so it won't be informative. So instead of that, we will compute the layer normalization of two numbers, which is the average and also 1 over I plus 1. So after layer normalization, the coefficient 1 over I plus 1 will be removed. And this will be a one-to-one representation of the sum. So we can check whether the sum is equal to the sum of the entire sequence by comparing the dot product of u, I, and u of the last token. So if the sum is equal, we have that their inner product is 1. If the sum is not equal, we have that the inner product is smaller than 1, strictly smaller than 1. So the inner product motivates the use of causal attention. So we can add the u sub v minus 1 to the query map and add ui to the key map. But how to retrieve the smallest such I? So we will need to use the fact that each value vi is either -1, 0, or +1. So note that if their inner product is smaller than 1, we in fact have inner product is at most this quantity, which is of order 1 minus omega 1 over the length of v to the 4th power. So this motivates us to use the following quantity, which can be computed in the positional encoding. So yeah, so let's compare two indices. If the dot product of I is equal to 1, but the dot product of J is strictly smaller than 1, we in fact have that their mutual difference is at most PV minus 1 over J plus 1 or I plus 1. So yeah, so we can use the query vector U and P and key vector U and 1 over I plus 1 in causal attention. And this will, together with hardmax, we will be able to retrieve the smallest such I. Okay, so I'm a little bit running out of time, so let me briefly introduce the time complexity here. So let function be a complexity function if it's non-decreasing and either Tn is a constant greater than 1 or Tn goes to infinity and then goes to infinity. So if theta of Tn is a complexity function, then time n Tn denote functions that can be computed by an n-type Turing machine in O Tn steps. And time Tn denote the functions that can be computed in Tn steps for any Turing machine, for some Turing machine. And P is the languages that can be decided in polynomial time. So we will show that two PTMs are nearly as efficient as Turing machines. So if we use one machine's DSW PTM, they will suffer from a polynomial slowdown over Turing machines. But in our construction, we will show that two PTMs have only at most logarithmic slowdown over Turing machines. So let's say from now on, let Tn denote a complexity function. And let time 2 PTM Tn denote functions that can be computed by a 2 PTM over Tn steps. So we show that first, for any time Tn function, it can be simulated by a 2 PTM in Tn log Tn steps. And in particular, for any functions that can be computed by a 2-type Turing machine in Tn steps, it can also be computed via 2 PTM in Tn steps. And then let's compute let's talk about the COT complexity class. So let COT sub gamma Tn be the class of functions that the constructed transformer can compute within OT and COT steps. So from the complexity results, we can show that any function that can be computed by two PDM in Tn steps can have most OT and COT steps, which is obvious from our construction. So yeah, so together we can show that for any time two function, time two Tn function can be computed in Tn COT steps. For general Tms, any time Tn function can be computed in Tn log Tn COT steps. And for complexity function Pn, let precision Pn be the class of functions that are, so the constructed transform can compute using OPn significant and guard bits. So here, yeah, so here we're following the convention in numerical analysis, where we assume that each floating point number has a significant bits and guard bits, where both significant bits and guard bits are used in our arithmetic operations, where guard bits are rounded off in numerical comparisons. Yeah, so here we show that any time Tn function can be computed in log n plus Tn precision. So in particular, P is in P function. So the P languages can be decided in log precision. So the sketch is basically we plug. So the total sequence length is the length of the prompt plus the length of the input plus the length of COT steps. So together it's n plus Tn log Tn. And attention similarities, since attention of similarity with mutual differences at least omega 1 over I to the fifth power. So this means that the Tn log Tn COT steps can be computed in log n plus Tn log Tn to the fifth power precision, and which is equal to the log n plus Tn precision. Yeah, that's pretty much I want to talk about today. And there are some future work. So which first we can show that maybe we can show lower bounds on the CLOP complexity and precision complexity. And maybe we can extend the theory for softmax instead of hardmax. Regarding context windows, so in practice, the trained transformers typically have bounded context windows, but our construction assumes infinite precision. So in particular, it will be able to compute infinite context windows. So it will be interesting to show expressive power under bounded context windows. And finally, our construction is an expressiveness result. So it will be interesting to show whether a corresponding learnability result exists or not. Yeah, that's it. Yeah, thanks for listening. And do you have any questions?